Start recording. Okay, so we've talked about what are what have we discussed so far? So we've discussed um, coterminal angles, and we've discussed radians and how it goes from degrees to radians, right? We talked about how pi radians is equal to 180 degrees. We know that. We know that coterminal angles are the same angles, just added by 360 or subtracted by 360 a certain number of times. And we're going to continue our journey into trigonometry by discussing more about angles. In particular, I want to talk about what are called reference angles. So what are reference angles? So reference angles are positive. So they have to be positive. That's the first thing. Second thing is it's acute. So that means that this is less than 90 degrees. And they're positive acute angles that are made between the terminal side and the x-axis or the horizontal axis. So these are reference angles, and let me tell you that these reference angles are very important for trig to understand it. So let's look at some examples of what I mean by that. So for example, let's start with an angle in the first quadrant, right? So remember, this is quadrant 1, this is quadrant 2, quadrant 3, and quadrant 4. So don't forget that, because it's also very important to remind ourselves every time. So if I were to have a terminal side in the first quadrant, for example, and the angle that I'm considering is the angle that's made between the terminal side. So this is the terminal side, right? This is the terminal side. Maybe I should write it like this. Terminal side. And it's the angle made between the terminal side and the horizontal axis. And it's the acute one. It's the smaller than the 90-degree angle. So what is the reference angle that we're speaking of? Well, it's exactly this angle here. This is my reference angle. So I'm going to call this theta REF. And let's suppose this is 43 degrees, for example. That would be my reference angle. So it's not really much to say here. But what if I have another one of these graphs here? And this time my reference angle, my angle, my terminal side is in the second quadrant. And the angle that's referred to this terminal side is 150 degrees. So as you can tell, this is not my reference angle. This is just an angle associated with the terminal side, but it's not my reference angle because my reference angle has to be acute, less than 90. So what's the corresponding reference angle? Remember, it's the angle that's made between terminal side and the positive x-axis, or not positive, the x-axis in general. So what is this angle? This angle right here, this is my reference angle. So how would you get the reference angle? (180 minus 50). Very good. Sorry guys, I didn't see. Do you guys hear echo? Is there an echo? No, okay. So yeah, so it should be, this is 180, right? This is 180 degrees. The whole entire thing, the whole first half is 180 degrees. And this is 150 degrees. So that difference here is the reference angle. So 180 minus 150, that's 30 degrees. So this is going to be 30 degrees, and that's the reference angle. Okay? Okay. Now what if I have another one of these little graphs here? And this time, my terminal side somewhere here. So I'm in the third quadrant now. What is this angle here? Well, let's say this angle is 240 degrees. What would be the reference angle? Remember, I want the angle that is between the terminal side and the x-axis, and that it's acute. So what I'm considering is this angle here. This is my reference angle. So if the terminal side goes around 240 degrees, and I want to find what's this missing angle here between the terminal side and the positive x-axis, how do I do so? How do I get the reference angle? If I'm in the third quadrant, I'm not going to do 180 minus 50. I'm going to do what instead? 240 minus 180. That's right. I do 240 minus 180 degrees. And that gives me 60 degrees. That is correct. And then finally, what if my angle, my terminal side, appears here in the fourth quadrant? And let's suppose that my angle associated with that, let's suppose this is 315 degrees. So I went 315 degrees around. What would be the reference angle? Again, the reference angle is the positive acute angle that's made between the terminal side and the x-axis. So what is that angle between the terminal side and the x-axis? It's this angle here. This is my reference angle. Exactly, Felipe, very good. So I want to find that missing piece. If I go all the way around, it's 360 degrees, but I don't quite get there, don't I? I get there 315 degrees. So then how many more degrees do I need to get that full revolution? So how do I do that? I do what? 360 minus 315. and that equals 45 degrees. So good. So that's the idea. The idea is that we're trying to figure out what is that angle that's made between the x-axis and the terminal side. That's it. That's all the reference angle is. So the reference angle will always be positive and will always be acute. Now I can also have negative angles. So for example, what would be this angle here? If I say this angle here is this theta is negative 30 degrees, what would be the reference angle? Remember, the reference angle is positive acute, made between the terminal side and the x-axis. Well, even though I went negative 30 degrees this way, it's still going to be positive in terms of the reference angle. Reference angle is still this angle here. It's still the same thing, except that's just going to be positive. That's going to be my reference angle as well. So you always have to be mindful as to what the angle they give you. And then you situate yourself in the quadrant. Which quadrant are you in? Once you're able to situate which quadrant you're in, then you're able to do the corresponding, finding out what the reference angle would be. So for example, let's do another one, and then we can move on from here. Let's see, 180. What if I do this? What if I make this angle here in the negative direction negative 120 degrees? Right, Chen, it's still going to be 60. Why is that? Because I want to find this angle here. I still want to find the reference angle. Remember, that hasn't changed. So if this is 120 degrees and all the way around is 180 degrees, right? Negative 180 degrees. If I'm going in the counterclockwise direction, pardon me, if I go into clockwise direction, these are all negatives, right? These are all negatives. If I go in the counterclockwise, they're all positives. So if I go in this direction, they're all negative. But I still want to figure out what is that angle that's made between this terminal side that goes negative 120 degrees to negative 180 degrees. How many more angles do I need in a way? How much more do I need? Well, I need exactly 60 degrees more. Okay? So again, the reference angle doesn't matter if my angles are negative, if they're positive. The reference angle will always be positive and it will always be acute, smaller than 90 degrees. Okay. So now, what happens though when my angle, for example, is in radians? What happens if my angle here is, for example, 14 pi over 15? How do you find the reference? You see this? How do you find that reference? What do we do? It's a 1 pi over 15. And how do I do that? It's the same idea as if I had degrees, except that now I'm using radians. Now, instead of using 180 all the time, I'm going to use pi. Because that's equivalent to 180 degrees. To get the reference, since I have this, right? This is pi. This is 14 pi over 15. So to get the reference, what do? I subtract pi minus 14 pi over 15. Or you can just notice that I need one more pi over 15 to complete the whole pi, for so to speak. So you get 15 pi over 15 minus 14 pi over 15. And my reference angle is pi over 15. And the same thing goes for angles in third quadrant, right? Instead of doing, so for example, let me give you one. So if I do, for example, what can I do? If I make this angle 13 pi over 10, so I'm dividing it into 10. If I do that, for example, I know I'm going to be in the third quadrant. And this angle here is my reference angle. And this angle here that's made halfway is pi. So if I went all the way to 13 pi over 10, and I want to find this missing reference angle, then I need to do what? I need to take this whole angle here and subtract it from pi. And then that difference would be the reference angle. So the reference angle here in this case would be 13 pi over 10 minus pi. To do that, I do 13 pi over 10 minus 10 pi over 10. And that gives me 3 pi over 10. That's going to be the reference. Okay? So the way we find the reference angle is dependent upon what quadrant you're in. If you're in the first quadrant, then the reference angle most likely will just be that angle, positive. If you're in the second quadrant, you would most likely have to do what? Pi minus the angle. If you're in the third quadrant, you would most likely have to do what? The angle minus pi. And if you're in the fourth quadrant, you had to do 360 minus the angle, or 2 pi minus the angle. So why don't we summarize that? So in summary, we find the reference angle to an angle theta, and make sure we say theta is between 360 and 0, or that theta is between 2 pi and 0. So make believe our theta, whatever it is between 0 and 360, and I want to find the reference angle to that theta. So if theta is in quadrant 1, then the reference angle equals theta. That's the first thing. Second thing, if theta is in quadrant 2, our reference angle is equal to 180 minus theta, or our reference angle is equal to pi minus theta. Okay, that's if I'm in quadrant 2. What if theta is in quadrant 3? The reference angle is going to be theta minus 180 degrees, or theta minus pi. Okay. And then lastly, if theta is in quadrant 4, then theta, the reference angle, is going to be found by subtracting 360 by theta, or the reference angle is 2 pi minus theta. Okay, so this is all we should really need for finding reference angle in a nutshell. Find what quadrant you're in, and based upon that, you make the corresponding appropriate operation to find the reference angle. And again, this idea of reference angle may not seem that interesting or that necessary now, but as we develop more of our repertoire and toolbox of trigonometry, reference angles become very important. Okay, so this is pretty much the foundation behind, or that what on what trigonometry stands upon. And I know many of you may have heard trig, right, about sine, cosine, tangent, and maybe you may have applied it to right triangles. So we're gonna talk about right triangles as well. But actually, to really understand trig, you need to understand circles. And it's very interesting the relationship that circles have with right triangles. It almost seems like they shouldn't have anything in common or anything that connects them, but they actually do a lot. And that's no more evident than in trigonometry. So we're going to first talk about the unit circle. Maybe some of you have heard about it before. This is very important. The unit circle. So what is the unit circle? Well, it's in the name, right? Unit. Unit means one. And what that means is the radius is equal to 1. That's one of the characteristics of the unit circle. The second characteristic is that the center is at 0, 0 at the origin. So that's what makes up a unit circle, the unit circle. The radius is equal to 1 and the center is 0, 0. Okay. So here we have it, our unit circle. And the coordinates here, right? The coordinates on the x-axis, we should know because it's centered at 0, 0. So my center is right here. And this is my x and y axis. And this coordinate right here is 1, 0. This coordinate right here is 0, 1. This coordinate right here is -1, 0. And this coordinate right here is -1, pardon me, 0, -1. Does anybody know the equation of the circle? I think we discussed this before, earlier in the semester, like in the beginning. Remember the equation of a circle is x minus h squared plus y minus k squared equals r squared. So in this case, the equation of the circle is one of the simplest ones. It's x squared plus y squared equals 1. X squared plus y squared equals 1. Okay, so that's the unit circle. So then you might be, but how does this even, why does this even matter? Well, it matters when we talk about triangles. Now, for right now, this may seem out of order, but you'll see how they all connect. So let's go to right triangles a little quickly here. We know about right triangles. It contains a right angle. Okay. And what do we know about right triangles? It has a right angle and it has the longest side. And the longest side is the hypotenuse, right? So this here would be the hypotenuse. The longest side in a right triangle. And then at the same token, we're going to be discussing what are called the 6 trig ratios. So we have something that's called sine, right? Call it sine of theta. And again, these are functions. SIN is a abbreviation for sine, SINE. So this is the sine function. And then we have the cosine function. This is cos of theta. Theta is an input. And then we have tangent. Tan parentheses theta. And then we have what are called the reciprocals. So these are the reciprocal functions here. Reciprocal trig. And what are the reciprocal trig? Well, this is cosecant function. Cosecant, which is equal to 1 over sine. The reciprocal of sine. And then you have what's called secant. The secant function, which is the reciprocal of cosine. And then you finally got what's called cotangent. And that's the reciprocal. Okay, so again, some of you may have seen this already, that's fine. But we need to make sure everyone's on the same page. So let's suppose I have this angle theta somewhere in the right triangle. And what we're concerned about are 3 sides. The first of which is the opposite side to theta, opposite, and it's 2 theta. So the reference point is the angle theta that you're dealing with. So the opposite to theta is that side there. So I'm going to call this ABC. This is ABC. So AB is my opposite side to theta. Then you have what's called the adjacent side, which is the side right next to it, to theta. So that's the adjacent side. So AC is my adjacent side. So AC is my adjacent side. AB is my opposite side. And then hypotenuse is BC, right? That's the hypotenuse, BC. It's that line segment BC. Now, what is sine? Sine of an angle is the opposite side over the hypotenuse. The cosine is the adjacent side. Pardon me. Is the adjacent side over the hypotenuse. And tangent is the opposite side over the adjacent. What is cosecant? It's just the opposite, or I should say the reciprocal of sine. So it's going to be the hypotenuse over the opposite side. It's going to be the secant, hypotenuse, over the adjacent side. And cotangent is going to be opposite, pardon me. It's going to be adjacent over the opposite side. Now I want to make a note on tangent. Note, tangent of theta is actually also written as sine theta over cosine theta. How is that possible? Well, what is sine theta? It's opposite over hypotenuse. What is cosine theta? Adjacent over hypotenuse. What happens when you take a fraction divided by a fraction? You multiply this first fraction by the reciprocal of the second fraction. The hypotenuse numbers here cancel. And then what's left with is opposite over adjacent, which is exactly the way it was defined earlier. Tangent is opposite over adjacent. So the important thing here is to also notice that tangent is the division of sine and cosine. And then in the same vein, cotangent of theta is the reciprocal of tangent. So it's just the opposite, right? It's the flip version of this. So it's going to be cotangent is cosine over sine theta. So that's just to keep in mind. Keep that in mind. So essentially what I'm saying is, if I know sine and cosine, I know everything. I know tangent, I know cosecant, I know secant, and I go to cotangent. So let's see this in action really quickly. So if we have a little example of a right triangle, and I'm going to give you one of the simplest right triangles ever. Three, 4, 5. So this is a right triangle. And how do I know this is a right triangle? What can help me? How do I know this is how do I know these side lengths make up a right triangle? How do I know? Does anybody know how you figure out whether the sides of a triangle make up a right triangle? It has to satisfy a very particular criteria. Well, you probably have heard this already. It's the Pythagorean theorem. It must satisfy the Pythagorean theorem. And what is the Pythagorean theorem? A squared plus b squared equals c squared. The c represents the hypotenuse. The a and the b are the legs of a triangle, not the hypotenuse. So in this case, 3 squared plus 4 squared equals 5 squared, question mark. Well, what is 3 squared? 9. What is 4 squared? 16. It's 9 plus 16. Does that equal 25? Yes, it does. So then we know it's a right triangle. So 3, 4, 5 represents sides of a right triangle. And how do I verify that? I use the Pythagorean theorem. Okay. Okay. So now, can I find the 6 trig ratios? What are the 6 trig ratios? Well, if I do sine of theta is what? Opposite over hypotenuse. So it's going to be 4/5. If I do cosine of theta, the angle theta, and for those of you, I just want to make a note as well. Theta, I think I mentioned this already, right? But theta is a Greek letter used for angles. Just want to make sure that's clear. So we're going to use theta a lot. What is cosine theta? Adjacent side. Oh, pardon me, guys. You guys should have pointed that out. The opposite side of theta is not 4, it's 3. The adjacent side of theta is 4/5. So what would be tangent of theta? Who can tell me what tangent of theta is? Remember, tangent represents the opposite side to theta over the adjacent side. So what would be the ratio for tangent? So be careful, Felipe. Tangent of theta is the opposite. Yeah, 3/4. That's what you meant. Yep. So the answer should be 3/4. So that's how you find tangent of theta, sine, cosine, and tangent of an angle if you have a right triangle. And then once you have these, you can get the reciprocal of them. So this is 5/3. Next one is 5/4. And this one, cotangent theta, will equal 4/3. So these are my 6 trig ratios. Sine, cosine, tangent, cosecant, secant, cotangent. Okay, let's see a few more things here. So what if I have something like this? 4, 5, theta. How do I find the 6 trig ratios for this one? So I want to find sine theta. I want to find cosine theta. And I want to find tangent. I know 2 of the sides, 4 and 5, but I don't know the hypotenuse. So how do I find the hypotenuse? I need to know the hypotenuse in order to find sine theta because I need to know what's opposite over hypotenuse. But right now, the hypotenuse is a question mark. So how do I find the side of the question mark? Right, Chen, I have to apply the Pythagorean theorem. So then I say, you know what? Let me call this C then, since we normally called the hypotenuse C. So then I use the Pythagorean theorem. Use Pythagorean theorem to find length of hypotenuse. So then I would say 4 squared plus 5 squared equals C squared. 4 squared is 16. 5 squared is 25. That adds up to C squared. 16 plus 25 is 41. But I want to figure out what is c, not c squared. In order to do that, I must take the square root on both sides of the equation to get rid of that square term. So I get c equals the square root of 41. That can happen. I can have radicals. And square root of 41 does not break down because 41 is a prime. So then we say c is square root of 41. So then what sine of that angle, theta? It's going to be the opposite side, 5, over the square root of 41. Cosine will be 4 over the square root of 41. And tangent will be 5/4. And then what's number 4? Cosecant theta is the opposite or the reciprocal of sine. So it's square root of 41 over 5. Then you got secant theta is square root of 41 over 4. And then lastly, cotangent theta is 4/5. And of course, if you want to rationalize, right, if you want to make the denominators rational numbers, then you have to multiply the top and the bottom of the fraction by square root of 41. And so you can also write this number as 5 square root of 41 over 41. That would have a positive, it would have a rational denominator. So again, these are equivalent. This is equivalent to this. These are equivalent. It's just that this is a rational denominator and this is not a rational denominator, and that's what we do to rationalize our denominators. So any questions about this? Finding sine, cosine, tangent, the reciprocal trig based upon a right triangle. Is that okay? Okay. No questions about that? All right, so we've touched upon right triangles and the unit circle. I'll only briefly talk about the unit circle. Actually, let me do one extra thing on right triangles. And it has to do with what are called Pythagorean triples. So I think this is something you should know about right triangles. Actually, there's another thing I also want to talk about in terms of right triangles. But Pythagorean triples are triples of whole numbers that satisfy the Pythagorean theorem. So the first one we discussed, the first triple, right? So these are my triples, okay? The first triple that we discussed is 3, 4, 5. Why is this a triple? Because 3 squared plus 4 squared equals 5 squared. 9 plus 16 equals 25. That is why. That is why we consider it a Pythagorean triple. And as you can see here, that's the first example that we discussed. 3, 4, 5 is the first one. But if you notice the second example, 5, 4, 5, rad 41, that's not a Pythagorean triple because square root of 41 is not a whole number. So having sides of a right triangle that are whole numbers like this is not that common. It's actually important or noteworthy to find out what numbers are whole numbers that make a right triangle, that make up the dimensions of a right triangle. So 3, 4, 5 is the simplest one of them. Now, once you have one, you have an infinite number of Pythagorean triples. And how do you get the rest of them? So from here, multiply every number 3, 4, 5, for example, by 2. So if I multiply every number by 2, what do I get? I get 6, right? 8, and 10. Now, is this a Pythagorean triple? We have to check. What is 6 squared plus 8 squared? Does that equal 10 squared? Well, what is 6 squared? 36. What is 8 squared? 64. That equals 100. Yes, indeed. 6, 8, 10 is also another Pythagorean triple. You see that? It satisfies the Pythagorean theorem. So I got 3, 4, 5, double it, and I get 6, 8, 10. What if I get 3, 4, 5 and triple it? What would I get now? 9, 12, 15. Is this a Pythagorean triple? Let's check. 9 squared plus 12 squared. Does that equal 15 squared? I get 81 plus 144. If you add that up, does that give me 225? Yes, it does. So look at this, guys. 9, 12, 15 is another Pythagorean triple that comes from the main root, 3, 4, 5. And I can do this on and on and on. I can quadruple everything, right? I can quadruple everything here. So I get what? I get 12, 16, 20, and so on and so forth. I can create a list, an infinite list of Pythagorean triples. And you can consider this as a root. This is like my root triple. And then these are all my leaves or offspring or whatever you want to call it. These are what comes after. I'll give you 2 more of these because there's actually a ton of them. These are not the only ones, though. We have other roots. So, for example, 5, 12, 13. This is another root. Why is that? 5 squared plus 12 squared, does that equal 13 squared? Well, 25 plus 144, doesn't that equal 169? Check. So I have another root. 5, 12, 13. It's not 5, 12, and 14. It's not 5, 12, and 15. It's not 5, 10, and 11. Those numbers don't work. But 5, 12, and 13, they work perfectly for the Pythagorean theorem. Then you can double that, and you get 10, 24, 26, and then you can go on, so on and so forth. You can just go on and on and on. So you should be able now to identify Pythagorean triples. And then the last one here is 7, 24, 25. And I can go on and on with this, but I'll just stop with these here. Because these are the common ones. Of course, if you double everything, you get what? 14, 48, 50. Yep, 12 squared plus 16 squared is 20 squared. That's right. That's this one here. That's true. The thing is, once you have one triple, like I said, you just multiply any number by those triples and you get a new triple. That's how you make more and more. But then you have different roots. 5, 12, 13, that's another one. 7, 24, 25. And I'll just give you a few more and you can check on your own. 8, 15, 17, that's another one. 9, 40, 41, that's another one. 12, 35, 37, that's another one. Some always escape me. But then yeah, these are the ones. 5, this is the 5th root, 6th kind of root here. You can check these on your own. I think, yeah, there's another one, I think, 11, 60, 61. Again, you can check these on your own time. And there's like an infinite number of roots and there's an infinite number of leaves. So there's a whole bunch of triples that exist out there. So these are just like some character. It's a characteristic of right triangles. Some of them have this idea that they're whole number side lengths. But of course, most of the time they won't be that simple. They won't be that nice, for example. Okay, so we discussed the Pythagorean theorem, we discussed right triangles, we discussed trig ratios, sine, cosine, tangent, and the reciprocal function, reciprocal trig ratios, cosecant, secant, and cotangent. We discussed Pythagorean triples, which pertain to right triangles. Now, before we even continue with the whole trig stuff, we have to also discuss what are called two special right triangles. And you must have seen this in your geometry class, if you've taken one. So we have two of them. They're called special. So the first one of its kind is the isosceles right triangle. What is the isosceles right triangle? It's the angle, it's the triangle that has what's called the 45, 45, 90 degrees. So that's the first of its kind. 45, 45, 90-degree triangle. That's a special right triangle. Now, this is called also a isosceles right triangle. Isosceles right triangle. It's isosceles, meaning that it has two sides that are the same, two bases that are the same. So these are the same. And we normally say this is side X. This side here is also X. Now, how do I find the missing side in terms of X? Well, we can apply the Pythagorean theorem. X squared plus X squared, that equals, I don't know, squared. X squared plus X squared, when you combine them, you get 2X squared. That equals the question mark squared. But I want to find question marks not just by itself, plainly. So I have to take the square root on both sides. And I get that the question mark is equal to the square root of 2x squared. But x squared here can be taken out of the radical, or I should say, I can take the square root of x squared, and that's equal to x. But rad 2 is just rad 2. So question mark, the hypotenuse is really the same thing as saying x rad 2. Now, what makes this special is that this always is true for every 45, 45, 90-degree triangle. It always has the ratio of these sides to be in this manner, x, x, x rad 2. So an example, if I know beforehand that I have a right triangle, and every angle, I have two angles that are 45 degrees, and I have one right triangle. And if I know one side, for example, is 5, then I know everything. If this side opposite the 45-degree angle here is 5, then the side opposite the other 45-degree angle is also 5 because they're isosceles, and because they're in this ratio, in this configuration for 45, 45, 90, then if one side, the smaller sides are 5s, then the hypotenuse would have to be 5 rad 2. And if you don't believe me, you can try it yourself with the Pythagorean theorem, and you still get 5 rad 2. That's why it's special, because once you know one of the sides, you know all of the sides immediately. That's only for 45, 45, 90. And then there's another one that you must know. And it's the 30, 60, 90 triangle. That's right, Chen. So what's the 30? The 30, 60, 90. So 30 is the smallest side. So let me make this a little bit bigger. Okay. So this is 30. So remember, the way angles work with triangles is that the smallest angle is opposite the smallest side. So 30 degrees is opposite the smallest side, which is this portion here. And then the next angle would have to be 60, and 60 is the second smallest side, right? So it's this side here. And then you have the right angle, which is opposite to the longest side, obviously. So the way this works is that this side, this thing here, actually, the way we construct a 30, 60, 90 triangle is if we had an equilateral triangle to begin with. And what do you know about equilateral triangles? All sides are the same, all angles are the same. So all the angles are 60 degrees. So let's say we have all the sides here are all 2x, right? All the sides are 2x. And let's make believe that I cut this equilateral triangle in half. So that means that this side here would have to be x because it's half of 2x. This side here is still the same side, right, as the equilateral triangle side. So this side here, this hypotenuse is still going to be 2x. Now the question becomes, what is the height? When I divided this in half, what is that height? How would I figure that out? Pythagorean theorem. So then the Pythagorean theorem states x squared plus question mark squared equals 2x parentheses squared. But what is 2x parentheses squared? It's 4x squared. X squared plus I don't know squared. I want to find what the question mark is. So I have to subtract both sides by x squared. So I get that I don't know squared equals 3x squared. Take the square root on both sides. And what do I get? I get the square root of 3x squared, but I can take the square root of x squared and it becomes x. So actually this here is x rad 3. And this is the configuration of the sides of a triangle, 30, 60, 90 triangle. It's x, x rad 3, and 2x. So as an example, what if I have, beforehand, I have the knowledge that I have a 30, 60, 90 triangle. And suppose I knew that one side of the 30, 60, 90 triangle, and I knew the 30-degree angle side. Let's say I knew that this was a 7. Then I should know all the other sides because it's every 30, 60, 90 triangle behaves like this one. So if the smallest side is 7, and that's x, so this equals x, you see that? Then what is x rad 3 going to equal? What's going to equal 7 rad 3? And then what is the hypotenuse going to equal? It's twice the smallest side. It's twice it. It's double it. So it's 14. So I should be able to figure out all sides of a 30, 60, 90 triangle. If I only know one of them, I should know all of them because I know the configuration of every 30, 60, 90 triangle. Woo! So we've been blazing through this stuff. Now, before we go back to unit circle, why do we care about these special right triangles? Well, because I know these special right triangles and I know a bit about trig ratios, sine, cosine, and tangent. Oh, and one thing I forgot to mention is a lot of people, they use this mnemonic device, this acronym, right? So, ka, toa. They use this just to make sure they can remember what sine, cosine, and tangent represent, right? So SOHCAHTOA is so, right? So I should write this here actually. So SOHCAHTOA. So this is so because it comes from SOH, sine, so. And then you have cosine, CAH. They're just the first letter of each of these ratios here. And tangent is finally TOA. So that's how they remember, or they should. This is a way to remember sine, cosine, and tangent. SOHCAHTOA. I just wanted to mention that. Now, why do I care about these right triangles? Is because now I can find a lot of things. For example, I can find what is sine. So let's go to ratios now, trig ratios. What is sine of 45 degrees? And what is cosine of 45 degrees? What's sine of 45 degrees? Well, sine of 45 degrees, I don't care if I'm in this triangle or in this triangle, sine of 45 degrees will always be the same. So let's look at this triangle here. 45 degrees, choose one of them. What's opposite 45 degrees? Isn't it x? What is the ratio, the hypotenuse of this right triangle? Isn't this x rad 2? What happens with the x's? Don't they cancel? So what do I get? I get 1 over rad 2. Sine of 45 degrees is equal to 1 over rad 2, period. And I could also rewrite this as a rational denominator. So I rationalize the denominator, and I get rad 2 over 2. That's important. Sine of 45 degrees is equal to rad 2 over 2. That's precisely what it equals. What's cosine of 45 degrees? Take the same angle, 45, and do the same thing, but now cosine is adjacent over hypotenuse. I still get the same fraction though. X divided over x rad 2, and that equals 1 over rad 2 multiplied by rad 2 over 2. And I get the same exact thing. Sine of 45 degrees equals rad 2 over 2. Cosine of 45 degrees equals rad 2 over 2. So I found the value of these trig ratios for these specific angle, 45 degrees. And I can apply the same reasoning for 30, 60, 90 triangles, right? I can say, hey, what is cosine of 30 degrees? What is sine of 30 degrees? What is cosine of 60 degrees? Actually, I should write this over here. And then what is sine of 60 degrees? So what's cosine of 30 degrees? Cosine of 30 degrees is adjacent over hypotenuse. So it's going to be what? X rad 3 over 2x. But what happens with the x's? Do you see how I don't really care about the x's? They cancel out every time. And then what is it? Rad 3 over 2. Cosine of 30 degrees is rad 3 over 2. What's cosine of 60? Go to 60 degrees. What's adjacent to 60? It's x. And what's hypotenuse? 2x. So then what's going to be the ratio is going to be x over 2x. But what happens with the x's? They cancel. So what's cosine of 60? It's a half. Cosine of 60 is 1/2. Sine of 30. Go back to sine of 30. 30 degrees. What's opposite 30 degrees now? Because I want to find sine. So it's x over 2x again. And I get 1/2. So you see here, cosine of 30 degrees does not equal sine of 30 degrees. Even though this might give you a feeling as if sine and cosine of the angles of the same angle is equal, that only happens for 45 degrees. For everything else, 30 degrees, they're completely different numbers. Hey, but they repeat though for different angles. So that's an interesting, there's a correspondence with those angles as well. Cosine of 60 degrees is 1/2. What's sine of 60 degrees? Go to 60 degrees. What's the opposite side? X rad 3. So I get the same thing as cosine of 30 degrees. And I get what? Rad 3 over 2. So cosine of 30 degrees is actually equal to sine of 60 degrees. Same. And then cosine of 60 degrees is actually the same thing as sine of 30 degrees. Make sense? Okay. So all of this is said about right triangles because I want to talk about the unit circle. So let's go back to the unit circle. What do I know about the unit circle? The center is 0, and it has a radius of 1. And I know the coordinates here. You see that? I know the coordinates here. I know this is 0, 1. Sorry. This is 1, 0. This is 0, 1. This is -1, 0. And this is 0, -1. Now, how in the world is a right triangle gonna even matter or be relevant for unit circles? Now, if you check this out, there's a point here, right? And that point has coordinates, x, y. So this is a point on the unit circle. Point on unit circle. Now, by the geometry of this, if I extend this point directly downward, perpendicular to the x-axis, not that perpendicular if I do that like this. So if I do it perpendicular to the x-axis, what do I form? I form a right triangle. And the angle that I'm interested in, so this, you start to see this? This starts to become what's called the terminal side, and we talked about this. And the angle that I'm concerned with is the terminal side and the x-axis, or in this case, the positive x-axis. So this becomes what? Theta. And then if we check the geometry to this again, the x-coordinate is how far away horizontally you are from the origin. So then that means that this side here can be considered as the x-coordinate, the x value. And then the y represents the vertical component. So if you want to look at this triangle once more, look what kind of triangle I have. I have a right triangle with theta, y, x, and 1 as the dimensions of my triangle. So then let's do one more thing. What is sine of theta? What is cosine of theta? For this triangle. So sine of theta. Why did that disappear? Whoops. Hold on. I don't know why that circle disappeared, but I'm glad it's back. What's sine of theta? Isn't theta opposite over hypotenuse? So isn't it y over 1? But y over 1 is y. That's important, guys. The y value of the unit circle represents sine theta. What's cosine of theta? Isn't cosine the adjacent side over the hypotenuse? So isn't this x over 1, which equals x? But isn't x equal to cosine theta? And this is how, in a sense, trigonometry is really comes to life. It's because of this. This is how you connect circles with right triangles. And when you do that, you have this whole field, this whole subject of trigonometry. So the unit circle has many points around it. And for every point you go around, it has coordinates. And those coordinates represent the angle that's made between the terminal side that connects that point to the origin and the positive x-axis. So without using the unit circle, using only the special right triangles, I can only find the angles for cosine of 30 I can only find the cosine and sine for 30 degrees and 60 degrees and for 45 degrees. But now that I made this connection with the unit circle, I can find it for any angle from 0 to 360 degrees. Do you see that? So for example, let's look at what happens when the angle that's made between the terminal side and the x-axis is 0 degrees. What happens if I'm in the 0 degree mark? So this is 0 degrees for me. And I have the unit circle. And the terminal side that I care about is this here. Well, I know this coordinates, right? 1, 0. But what else do I know? I know that, what? X equals cosine theta. Y equals sine theta. What is theta here? What is theta? Theta is 0 degrees. And my x coordinate is given by what? Cosine of 0 degrees. And my y coordinate is given by what? Sine of 0 degrees. So based upon the unit circle, what could I figure out? I could figure out that cosine of 0 degrees is equal to 1 by the construction that I just made. And sine of 0 degrees has to be 0. Do you see that? It's because of the connection that I made between the x and the y's and the angle. So because I know the x and the y coordinate, then I immediately know what cosine and sine is. And that's how circles become so useful, particularly the unit circle. Let's look at the other example here when we have a unit circle. And now let's look at what happens when my terminal side with the positive x-axis, right? My terminal side is now a 90-degree angle. So this is my theta. What if my theta is 90 degrees? What's the coordinates? The coordinates of the terminal side to the unit circle, right? The coordinates is 0, 1. But what does 0, comma 1 represent again? 0 represents the cosine, because that's the x value, right? This is the x. Cosine of what angle? 90 degrees. And what does y represent? Y is the value 1. 1 represents what? Sine of 90. So then what did we just discover here? I discovered that cosine of 90 degrees and cosine of 90 degrees is 0 and sine of 90 degrees is 1. Hope you guys start to see the connection between sine and cosine and the x coordinate and the y coordinate on the unit circle. And you can go on and on. You can go, what happens when the terminal side is 180 degrees? You see that? What if my angle here with the terminal side is -1, comma 0? This is the point. And this angle that's made, right, between the positive x-axis and the terminal side is 180 degrees. So that is theta. -1, comma 0. Remember, the x-coordinate represents, -1 represents cosine of the angle, which is 180 degrees. Y is 0, represents sine of the angle. What did I just discover? Cosine of 180 degrees is equal to -1. Sine of 180 degrees is equal to 0. Is everybody following this? Does this make sense? Does this make sense with the right triangles? Trig, right? And these angles here? Yeah, just making sure everybody got this. So we can start making tables now. So remember we talked about reference angles and they have to be positive, right? So now we can create a table of our reference angles. So we have 0 degrees or 0 radians, right? We know what those values are. We know that for what? For sine, cosine, and then we're going to talk about tangent eventually. We know 0 degrees. We know 30 degrees. But of course, that's also pi over 6 radians. So that also works for radians. But for now, we've only done degrees to simplify things. Pi over 4 radians. We also have 60 degrees. Which is pi over 3 radians. And then we have 90 degrees. which is pi over 2 radians. Sine of 0 degrees, didn't I find that already? Sine of 0 is 0. Sine of 30 degrees, or pi over 6, we found that with the right triangle here. Sine of 30 degrees is a half. Sine of 45 degrees we found to be rad 2 over 2. Sine of 60 degrees is rad 3 over 2. And finally, sine of 90 degrees is 1. And then we can fill out the next row. Cosine of 0 degrees is 1. Cosine of 30 degrees is rad 3 over 2. Cosine of 45 degrees is also rad 2 over 2. Cosine of 60 degrees is 1/2. And cosine of 90 degrees is 0. If you notice, these numbers here go in ascending order. And then we just go right back down and go in the opposite reverse order here for cosine. So these are the angles, guys, that you should have all in your head, stored in your head. All of these here you should have in your head, and all the sine and cosine you should have in your head. As you start using this more and more, this will become part of your daily activity with trig. Now, how do you find the values for tangent? Remember, tangent was sine over cosine. So you just have to take the values for sine and cosine and divide them to get tangent. So tangent of 0 degrees is going to be 0 over 1. What is 0 over 1? It's 0. So tangent of 0 is 0. What's tangent of 30 degrees? Sine of 30 degrees over cosine of 30 degrees, which is 1/2 divided by rad 3 over 2. But what is 1/2? So you know what? Let me write this out somewhere else. So now let's look at tangent really quick. So what's tangent of 30 degrees? Tangent is sine of 30 degrees over cosine of 30 degrees. But what's sine of 30 degrees? 1/2. What's cosine of 30 degrees? Rad 3 over 2. When I take 1/2 divided by rad 3 over 2, I get 1/2 multiplied by 2 over rad 3. The 2's cancel, and I get 1 over rad 3. But I don't want to leave it as a rational denominator, so I multiply top and bottom by rad 3 over 3. Rad 3 over rad 3. And I get rad 3 in the numerator, and rad 3 times rad 3 is 3. So this is rad 3 over 3. So tangent of 30 degrees is rad 3 over 3. What's tangent of 45 degrees? It's the same idea, right? Sine of 45 degrees divided by cosine of 45 degrees. Sine of 45 degrees is rad 2 over 2. Cosine of 45 degrees is rad 2 over 2. But rad 2 over 2 divided by rad 2 over 2, anything divided by itself would be 1. So tangent of 45 degrees, tangent of pi over 4 is 1. And then we just continue on our way, right? We continue. Tangent of 60 degrees is sine of 60 degrees divided by cosine of 60 degrees. What's sine of 60 degrees? Rad 3 over 2. What's cosine of 60 degrees? 1/2. You get rad 3 over 2 multiplied by 2 over 1. The 2's cancel, and I get rad 3. Remember what I said. Once you know sine and cosine, you know everything. You know tangent, you know cosecant, secant, and tangent, and cotangent. And finally, the last one. What is tangent of 90 degrees? Isn't it just sine of 90 degrees over cosine of 90 degrees? So isn't it 1 divided by 0? What is 1 divided by 0? Can anyone tell me what is 1 divided by 0? 0? So if you have 1 pizza and you divide it among 0 people, they get 0 pizza. It's undefined. This is when the division doesn't make sense. You can't divide by 0 because it makes no sense to divide by 0. Right? That's where division breaks down when you divide it by 0. You can divide by any other number. It doesn't matter how small, how big. But the moment you divide anything by 0, you're in no man's land. Okay, very good. So we know our reference angles, and we know the sine, cosine, and tangent for these angles. Okay. Great. Great. So now that we know that, what happens if I want to find, for example, find the value of sine of 150 degrees? How do I do that? If you notice, these angles are all acute for the most part. And we saw a little bit how we can go further than acute. We can go 180, we can go 270. But what if I'm at 150 degrees, for example? Still go back to the unit circle. I'm at 150 degrees, right? So I'm almost to 180, not quite. And I have this triangle here. Or the terminal side, I should say. And this angle here is what? 150 degrees. And what do I know about the x and y coordinate on the unit circle? It's also known as the what? Cosine of 150 degrees, comma, sine of 150 degrees. It's the same, right? It's the same. Now, because of the symmetry, this is where symmetry is beautiful. There's symmetry across the y-axis, isn't there? The same way there would be across the x-axis. It's symmetric around because it's centered around the origin. That's important. It's centered around the origin. Because of the symmetry of a circle and it's centered around the origin, then isn't there another triangle on the left side that's like literally identical? It's just a mirror image, isn't it? And then I'm going to say, hey, don't you guys remember we talked about reference angles, and the reference angle of 150 is what? Isn't it this angle right here? This is 30. By the symmetry, isn't this also going to be 30? Don't we know everything we need to know about this one here? What is this point here for this segment here? That's 30 degrees away. Don't we know everything about this? The x comma y coordinate. Don't we know that this is equal to cosine of 30 degrees, comma sine of 30 degrees? Don't we know cosine of 30 degrees is rad 3 over 2? Don't we know that sine 30 degrees is a half? So don't we know that the coordinates of this point, if it's 30 degrees away from the x-axis, positive, isn't this point right here going to be the coordinates rad 3 over 2 comma 1/2? So by the symmetry, if I reflect this across the y-axis, which coordinate do I have to negate? And which coordinate do I just leave? If I reflect that across the y-axis. Do you see that? Do you guys understand what I'm asking? This point right here is just the mirror image of this point right here. I know the coordinates of this point. I just reflect this across the y-axis. I reflect it. So what happens? What is this point now? What are the coordinates of that point? Isn't it going to be negative rad 3 over 2, comma 1/2? So sine of 150 degrees is actually the same thing as sine of 30, which is 1/2. And then in the same token, look what I found. I found cosine of 150. Cosine of 150 degrees is not positive rad 3 over 2. It's actually the negation of cosine of 30 degrees, which is negative rad 3 over 2. So this is where reference angles come back into the mix. And the idea is this. The idea is that in the quadrants that we care about, trig functions are positive and negative in certain quadrants. And we use this another acronym called ASTC. All students take calculus. What is it saying? What does it really mean? It means that all the trig functions are positive. So sine of the angle in the first quadrant, positive. Cosine, positive. Tangent, positive. They're all positive because x and y are all positive. In the second quadrant, only sine is positive. Everything else is negative. Cosine is negative, tangent is negative. Only tangent is positive in the third quadrant. And then only cosine is positive in the fourth quadrant. And it has to do with what? Why is this true? It has to do with what? X equals what? Cosine of theta. Y equals what? Sine of theta. And what does tangent equal? Tangent, remember, is sine over cosine, so it's y over x. In the first quadrant, all the x and y values are positive, so everything else is positive. In the second quadrant, only the y coordinates are positive, the x coordinates are negative. So sine is positive, so only sine is positive. Everything else has to be negative. In the third quadrant, the x coordinates and the y coordinates are negative, so only tangent is positive because a negative divided by negative is positive, but each of these individually will be negative. And in the fourth quadrant, only the x values are positive, the y values are negative, so those signs are negative, tangent is negative, but cosine is positive. That's how it works. So to figure out sine, cosine, tangent of other angles outside of the first quadrant, I need to first figure out what quadrant I'm in, figure out which one of these trig ratios are positive or negative in that quadrant, and then I have to refer back to the reference angle. And that's how you find the rest of these angles. So for example, find the value of sine of 240 degrees. For example, so the question one you ask is, where is, or in which quadrant? is 240 in, 240 degrees in. So what quadrant am I if I'm in 240 degrees from 0 degrees, from the positive x-axis? What quadrant am I in? Anybody? I'm in quadrant 3. Great. Second question I asked myself, is sign positive or negative in quadrant 3? It's negative. Why? Because only tangent is positive in quadrant 3. And then the third question I asked myself is, what is the reference angle? If your angle is 240 degrees, how do you find a reference angle? We did that earlier, right? What is our reference angle? Anybody? Our reference angle is for 240 degrees, guys. We did it. If it's in the third quadrant, to find a reference angle, don't you take 240 subtracted by 180? Don't you get 60? That's right. Now put all these three things together and look what I get. Sine of 240 degrees is negative because it's in quadrant 3, and it's equal to the negative sine of the reference angle, which is 60. I go back to the reference angle. What's sine of 60 degrees? Rad 3 over 2. So sine of 240 degrees is negative rad 3 over 2. You guys see that? I hope that makes sense. And this is all you have to do for all of them. For any kind of function that you find. So for example, if I get tangent of 330 degrees, what is that equal to? First, figure out where is tangent. The 330 degrees is in what quadrant? 1, 2, 3, or 4? Anybody? What quadrant am I in, guys? If I'm 330 degrees, I'm in quadrant 4. Good. Tangent is what? Positive or negative? In quadrant 4. Negative. So this will be negative. And then what's the reference angle for 330 degrees? 30. Very good. So tangent of 330 degrees is equal to negative tangent of 30 degrees. Tangent of 30 degrees is rad 3 over 3. So this is my value for tangent of 330 degrees. I found out what quadrant I'm in. I found out whether I'm positive or negative, and I found out what is the reference angle. Because every other point, remember the unit circle. Always remember the unit circle. It comes back to this. If I know all my points here, then correspondingly, I would know all the points here because it's just positive or negative depending upon what quadrant I'm in, which is how we saw this, right, in this first example. So 30 degrees here, we know sine and cosine of it, right over 2, 1/2. 150 is just a reflection across the y-axis. It's just symmetric. So it's based upon the reference angle. Okay? That's how you find the values of the different trig functions. And now, before we finish, I need to show you one extra thing. So this is when you want to find the values of all 6 trig functions if you know one, if you are given only one of them. This is a common thing that I'm going to test you on. So for example, if sine of theta is -4/5 and theta is in quadrant 4. So let me just write that down here. So I have a unit circle and my angle of some sort is here. And I have an angle theta, 4th quadrant. I want to know what's cosine. I want to know what's tangent. I want to know cosecant. I want to know secant. And I want to know cotangent. What's the first one I can find immediately? Well, if I know sine, I know cosecant. It's just a reciprocal. So that one's quick, -5/4. But how do I find what cosine is? Well, what's going to help me is I know that the angle's in quadrant 4. So then what do I know about cosine? Cosine has to be positive in quadrant 4. Tangent has to be what? Negative in quadrant 4 because tangent is only positive in quadrants 1 and 3. Secant has to be positive because that comes from cosine, and cotangent has to be negative. So once I've established that fact that the angle, the quadrant gives me the sine of my angle, the sine of my value. And now, how do I take care of this guy? Sine of 4/5. So what I have to do is I have to create a right triangle again. And this right triangle, right, has certain dimensions. Remember, 4/5, sine of 4/5. So then what I could do is I can create a triangle. So create a triangle whose angle here is theta, whatever that is, right? And if I have sine of theta is 4/5, in this case, I'm not going to worry about the negative because I already took care of the negative due to the fact that I know the angle. If sine of theta is 4/5, then I would know the opposite side. I can create a triangle whose opposite side is 4. And the hypotenuse would have to be 5. But we already saw this triangle. It's 3, 4, 5 because it's the Pythagorean triple. So then what would be the cosine of this angle? Cosine would be adjacent over hypotenuse. 3/5. Tangent would be what? Opposite over adjacent. 4/3. Secant would be the reciprocal of cosine, 5/3, and cotangent would be the reciprocal of 4/3, which would be 3/4. So I found all the rest of my trig functions based upon the one they give me and based upon what quadrant theta lies in. So remember, the quadrants, that gives you the sign of your trig function. And the actual value, you can find the rest of them by creating your own right triangle with those dimensions and finding the missing side. Alrighty. So I think we'll stop here.